Welcome to the Cosmic Savannah with Dr. Daniel Kahneman.
Dr. Jacinta Delhaze.
And Dr. Tiamiso Makwela.
Each episode, we'll be giving you a behind-the-scenes look at world-class astronomy and astrophysics happening under African skies.
Let us introduce you to the people involved, the technology we use, the exciting work we do, and the fascinating discoveries we make.
Sit back and relax as we take you on a safari through the skies.
Welcome. Who noticed something different?
Welcome to Season 5, everybody. Yeah, we are back in the studio for the first time in 3 years.
Yes.
Which is insane. Today we have a super exciting episode for you. We've got a surprise guest, one of the biggest names in astronomy. We're not going to introduce it just yet. You may have also noticed another additional surprise to this season. We have a new host. Welcome.
Welcome.
Thank you. Thank you for having me, Jacinta and Danielle, and I'm really happy to be joining the Cosmic Savannah.
Yeah. Okay, so who are you? Do you want to introduce yourself to our listeners?
Yeah, I am Dr. Tiamiso Makwela. I got my PhD, now it's a year ago. Wow.
Yeah, time flies.
It does. And I did my PhD in astronomy education research at the University of Cape Town. And I've been focusing on ways in which to make our own institutions and our astronomy departments more inclusive through astronomy education and making our own introductory classes be more kind of inviting to our students. Because, our students run away from doing astronomy because, it is really big.
Things are big.
Yeah. Then you're an excellent addition to our crew. We're trying to get people into astronomy at every level and not just at the university.
We're extremely happy to have you, Tia. So can you tell us, first of all, where are you from?
Okay, so I am from Diepkloof in Soweto. So yeah, I'm one from Soweto. They're saying Soweto in the ghetto. And that's where I grew up. I went to schools in Soweto, in Diepkloof, and then proceeded to go to Wits University, which is in Johannesburg. And also coming from Diepkloof, going to Wits, becomes a big deal. And when you are at Wits, then you're just really scared if you can actually make it out of there. Make it out of there with everything still in place, your mental health, your
sanity,
mind, your sanity.
Yeah.
And when I was at Wits, the saying was, Wits gives you the edge. And that used to just scare me a lot. And I needed to get out of there as soon as I could, but I didn't. It took me 7 years to get out of Wits. And then I came to UCT to then do my PhD at UCT. So that is kind of a little bit about me and a little bit about my journey. But yeah, I'm from the ghetto.
The only thing I know about Soweto, being a foreigner, ignorance, is that they have amazing music from there. And I have this record, an LP from Soweto swing music, and it's amazing.
So you finished your PhD last year, 2022?
Yes, 2022.
And what have you been doing since then?
So I was kind of in a transition period already in my PhD. So I started my postdoc before I actually finished my PhD.
It's always good to do two things at the same time. Two extremely stressful things at the same time.
Yeah. And so I've been doing my postdoc with the OAE. So the OAE is a sister office to the OAD, the Office of Astronomy for Education, which is hosted in Heidelberg at MPIA, the Max Planck Institute of Astronomy. And it has a center for education there, and I do my postdoc with them, but I am working with them remotely from South Africa. So for the last year, I've been doing my postdoc. So postdoc is PhD 2.0.
It's what comes after.
But also in my postdoc, I get to do other things, which is what excites me about my postdoc, that I get to work in projects that I've never thought I'd work in, and international projects as well, and working with different groups of people around the world and supporting their different missions in astronomy education. So that's what I've been doing.
Okay, thank you, Sia, for introducing yourself. It's very exciting for us to have you here with us. And as part of the team, we're really looking forward to working together in the future and making the Cosmic Savannah even greater.
Yeah.
I'm excited to be here.
Hopefully the gusto levels, if you're Australian, will be up, and the gears levels will be up.
The
what? South African. Oh, goodness. See,
I don't know
Tia
what's going on.
No,
now I'm the odd one out.
Say gears.
Yes.
Yeah, so it's like spirit, energy.
Okay.
Yeah.
Good.
Yeah, it's South African. Gusto, I think, in Australia. The equivalent.
Right. Okay, all right. And so we are all three of us squeezing into our tiny, tiny little studio, which Dan and I spent a long time yesterday getting new furniture for and rearranging so that we would all fit. And so, yeah, exciting to be back in studio for the first time in 3 years. Each episode, we will be probably having at least two of us hosts, maybe all three. It's going to be a surprise for you. It's going to be a surprise for us. You'll hear in the introduction who you're going to have today as hosts, but, one of us might be away or whatever, so there'll be a nice little rotation. Okay, so now I guess we can move on with today's episode.
Yeah, before we do that, some exciting things happening in astronomy. We haven't chatted to you for a while. We did have our interseason special where we updated you on what we've been doing and some of the exciting things that have been happening in astronomy. But just in the last few weeks, some really, really cool discoveries and events. The first one being the Euclid Space Telescope getting rocketed off into space.
Yes, so this is a long-awaited observatory, which is a satellite needed to be launched into space, and it's finally happened.
I think that's really cool to see what the discoveries of it will be.
Yeah, so Euclid's mission is to explore what they call the dark universe. So it's getting sent out to L2, which is the Lagrangian point 2, where James Webb actually sits, and it's about 1 million kilometers away from Earth. So it's not orbiting us and it's not coming back. And it has a 1.2 meter mirror and a couple of instruments, an optical imager, and as well as an infrared spectrometer and something else, photometer. Yes, so it can measure the brightness and the spectra of galaxies. And what it's going to do is map a quarter of the night sky, which is a lot still, over the next 5 or 6 years as its mission. And it's going to be able to work out the position speeds of these galaxies, and we can work out how the universe has stretched and expanded over its history.
Yeah, so we basically want to be able to really accurately measure the positions of these galaxies in space, and therefore we can find the distances between them, and through a whole bunch of very complicated equations to do with cosmology, we can find out some stuff about this dark part of the universe, dark matter and dark energy.
And maybe we'll have some new discoveries.
I'm excited for the new discoveries.
Yeah.
We'll have to, yeah. So I think Euclid will start getting results probably in 6 months or so. I think they're the same as James Webb. There's a large calibration period, sending a satellite to space and making sure everything didn't get wobbled out of place in a rocket launch.
We wait with bated breath.
And there's been more exciting news on gravitational waves.
Yes, so gravitational waves, first detected in 2015 after being predicted more than 100 years before by Albert Einstein and general relativity. So when very dense objects merge, things like black holes, they warp space and time and send out ripples, like ripples in a lake when you throw in a big rock. And in 2015, using laser interferometers, this was detected for the very first time. So these laser interferometers are big detectors which have a very long, 4-kilometer long arm at right angles to each other. The light is beamed along these 4-kilometer arms and back. And if there's a slight shift in the phase of the light, you can detect whether a gravitational wave has passed through the Earth, and space and time is bending slightly, right? As are we, but we can't really feel it. But it passes through everything.
I mean, it's bending by something like less than the size of an atom.
It's 10 to the minus 18 meters.
That's really small.
Right, and there's been an experiment being done to try and detect a kind of a background noise or background whir, essentially, of gravitational waves in the universe using something called pulsars. And pulsars are one of the results of the death of a massive star. So you have a huge star dying in a massive supernova explosion. What can be left at the end of that is perhaps a black hole or perhaps a neutron star, which is basically all of the matter has been condensed into only neutrons, so protons and electrons squished down into forming just neutrons. This is an extremely dense object. Sometimes they can be rotating, sometimes they can be releasing these pulses of radio light, and when they do that, they are called pulsars.
Yeah, so these pulsars are beaming in radio wavelengths, and they're a little bit like a lighthouse. So they are spinning incredibly rapidly. Some of them are, milliseconds. So you're getting these pulses every millisecond or so. And they are some of the most accurate clocks in the universe. They're incredibly stable. They do sometimes go through glitches, but most of them are incredibly stable, or for a long period are stable. And we can use them as independent measures of time. And if you have an independent measure of time, then you can start saying something about space. So what has been done is these 67 of these pulsars have been monitored for about 15 years, and these times have been accurately mapped and correlated. And what astronomers have found is that they can actually detect this background gravitational hum from merging black holes, or sort of the remnants of a merger event, and possibly the background gravitational wave from the Big Bang. Right?
That's so cool.
Yeah, very, very cool. So this is independent now to laser interferometry. We're using radio telescopes to detect gravitational waves. At the time, we were very excited because we got this new sense, this new way of exploring the universe, and now we're expanding on that using different telescopes. And this is going to be something that SKA can contribute to.
Yeah, this is a really big deal, really, really massive finding. And we have actually done a few episodes in the past on pulsars. We spoke to Dr. Marissa Heyer, and we also had another episode with Katya Moskovich and Matthew Bales. Matthew was involved in this discovery, I'm pretty sure. I can't remember those episode numbers off the top of my head, but we will put links to them in the show notes. And if you want to know more about pulsars, you can have a listen to those episodes. Or you can keep listening to this episode where we have a very special guest.
Go on, Jacinta.
Thank you.
Tell us who.
Okay, I'm bursting at the seams here. All right, so recently I have just come back from the University of Oxford, where I spent a month working with some collaborators. This is in the UK. And while I was there, I bumped into someone very special, none other than Professor Jocelyn Bell-Burnell, who very famously discovered pulsars. No big deal, but discovered pulsars in the 1960s. And also very famously did not win the Nobel Prize for this discovery. Her supervisor and another person won the Nobel Prize, and she was excluded. And Jocelyn is just one of the most amazing astronomers and the most amazing people I've ever met, a personal hero. I was just so excited and so honored to be able to speak with her. And she told us all about her life story, the struggles that she had to go through, what she overcame, and the whole story behind the discovery of pulsars, and also her amazing work in outreach, science communication, and also her passion for increasing the diversity of people in physics and astronomy. She won a massive prize from the US recently, a few years ago, and it came with a $3 million prize money, which she donated all of to scholarships for increasing diversity for women and minorities in physics and astronomy, which is just
Yeah, that is really great, actually.
really awesome.
Yeah, incredible. I think she's widely known in the astronomy community, one of the most famous astronomers there are. And, as you said, not just for discovering pulsars, but for so much else besides. She's really contributed a lot.
I think it's also good to mention that she built the telescope, right?
Yeah.
And I think that's really great because not so many astronomers are actually involved in the building of telescopes, and we use telescopes, right?
Yeah, so she really knows from the ground up, literally, what's going on with this instrument. I'm sure that helped her to make this discovery.
Yeah, absolutely. Very exciting, and very jealous that you got to speak to her.
Yes, it's really exciting. Shall we take a listen?
Yes, please.
With us today, we have Professor Jocelyn Bell-Burnell with us. Welcome to the Cosmic Savannah, Jocelyn.
Thank you very much.
We're very excited to have you here. Please, could you just first introduce yourself briefly to our listeners?
My name is Jocelyn Bell-Burnell. I'm an astronomer, or if I want to be a bit more scary, an astrophysicist.
So we are sitting here at the University of Oxford. What's your role here?
I'm a visitor here. I'm supposed to be retired, but they give me desk space, office space, and I can join in all the activities here.
Great. You've been visiting for quite a while, haven't you?
Indeed, yes.
And have you ever been to the African continent?
Yes, I've been to Africa several times.
Oh, great. Where have you been?
Most recently to Ghana. I've also been to South Africa. I've been to Kenya, Burundi, I think, from Kenya.
For holidays or for work?
No, it's all been work.
Right. Okay, great. What sort of things have you been up to?
The Kenya and Burundi stuff was for Quakers, my church. There are a lot of Quakers in Kenya. The visits to Ghana and to South Africa have been for science, for astrophysics.
Okay, awesome. So let's start talking about that. How did you initially get interested in physics and astronomy?
I knew at school that I was good at science. I can remember very vividly, I was probably about 12, and at school we are learning about particles going round in circles, circular motion, angular motion. My father's very widely read. He's brought home a book from the library about astronomy, and I have borrowed this book and removed it to my bedroom for reading. And in the book, I'm reading about galaxies and the way galaxies go round. And I suddenly realised the stuff we're doing in science at school can be applied to galaxies.
Oh, wow.
That's great. I'll be an astronomer.
Yay! Okay, awesome. So then what did you do from there? How did you make your way into a career in astronomy?
Well, I continued good at science at school, and by school leaving, I was doing maths and physics. We specialised quite early in Britain, probably too early. But anyway, I'd done lots of maths and physics. I was still keen on being an astronomer, but I decided to do a physics degree at university because if I couldn't get to do astronomy for any reason, well, there'd be lots of other things you could do with a physics degree. So I went to the University of Glasgow in Scotland and did a physics degree.
Wonderful. And did you face any challenges in getting started with this career?
There were 50 of us, 50 of us in the honours class the last 2 years at university, and I was the only female. So it was a bit lonely. And also at that time in Glasgow, it was the tradition, you see that word in inverted commas, it was the tradition that when a woman entered the lecture theatres, all the men whistled, stamped, catcalled,
Oh, no.
made as much noise as they could. And the way women in the university managed that was they'd gather outside the lecture hall and then enter in a group.
Right.
But as the only female in the honours physics class, I didn't have a group. So I had to face that on my own.
Oh, dear.
It did test whether I was sure I wanted to do a physics degree, and I did. So
Yeah, you persevered through that. Well, we're very glad that you did. So congratulations on that. You know, that in itself is a huge achievement, I think. So, okay, so then you did your degree in physics, and then what happened after that?
I decided I wanted to study astronomy, and the route into that is to do a higher research degree called a PhD. I had originally hoped to go to Jodrell Bank because I'd worked there one summer, but they did say they weren't sure they'd take women students,
Oh, dear.
and they never replied to my application, so I thought that's them not taking women.
So where is Jodrell Bank for our listeners?
Jodrell Bank is part of the University of Manchester. It's in the countryside way outside Manchester because in order to do radio astronomy, you need places with little radio interference. So it's out in the countryside.
Right, okay. So you didn't go to Jodrell Bank.
I didn't go to Jodrell Bank. I thought I'll never get into Cambridge. I'm not bright enough. I'm probably going to have to go to Australia. But the academic year in Australia doesn't start till January
Right.
or February. I have some time in hand. I'll put an application into Cambridge just in case.
Right. Well, Australia's loss. All right, so you started a PhD at Cambridge. What were you working on there?
This was in radio astronomy, which is the branch of astronomy I had identified. And within the first week of arriving, you get assigned to a project. And my particular project was one to find more quasars, quasi-stellar radio sources. They were a very hot topic at that point. There were probably only about 20 of them known. They were known to be very distant, but also very bright radio sources. And that seemed a bit of a contradiction. Distant things are usually faint. So they were clearly very curious objects.
And how did you go about starting to study these quasars?
They are very compact objects, which means they were susceptible to twinkling as the radio waves came through the space, particularly the space between the sun and the planets. So we decided to exploit that technique as a way of picking out the quasars, but it meant we had to build a huge radio telescope. And for the first 2 years of my 3 years research, I was building a radio telescope.
By hand?
By hand, along with about half a dozen other people.
Wow. Okay, tell us about that experience.
It was huge. In British units, it was 4 acres. That's 57 tennis courts.
That's
in
huge.
size. Thousands of wooden posts to hold all the antennae up out of the wet grass, and kilometres of copper wire and stainless steel wire. My particular job was all the junctions for the cables. Can't remember now how many cables I put plugs and sockets on, coated junctions in blocks of araldite to keep the weather out and that kind of thing. But I also did a certain amount of sledgehammering.
Sledgehammering?
Yeah, because I had to hammer posts into the ground.
I guess if you had a frustrating day, that would be quite therapeutic.
I actually became quite strong.
Yeah.
I was playing field hockey at the time, and I could hit the hockey ball from one end of the pitch to the other. I was so strong.
Wow.
My team didn't appreciate it. They'd watch the ball go past and say, "Oh, Jocelyn, you don't expect us." You know.
Wow, some unexpected skills out of astrophysics there.
Yeah. Oh, yeah. Yeah.
Okay, so you're building this radio telescope, and then did you eventually get it working?
Yes. Once it was built, the rest of the construction crew moved on to other projects, and I was left to make sure it worked and then use it. And unusually for a radio telescope, it worked the first time it was switched on.
Wow, that is quite unusual.
So that saved a lot of time.
Yeah.
So within a week of it switching on, I was busy finding quasars.
Wow, and did you find any quasars?
I found hundreds, yes.
Wow,
Yep.
cool. Okay, and what does a quasar signal look like?
A quasar is a very compact object. It's galaxy mass, but it's much, much more compact. We now know because it's got a great big black hole in the middle. Quasi-stellar is the full name. They look to optical astronomers a bit like stars until you realise that they're at huge distances. They're way, way beyond our galaxy. They're some of the most distant things known in the universe, with these massive black holes in the middle. And the black holes can be quite active, so they erupt every so often. They burst, they send out flashes and so on.
So you're going to see flashes in your radio telescope?
Not so much in the radio, to be honest. What I am seeing in the radio is that as the radio signal comes to Earth through the space between the sun and the planets, it meets a lot of irregular plasma blowing out from the sun. And that makes these sources change their brightness. Scintillate is the technical word. Whereas radio galaxies are much broader things and they don't suffer the same scintillation. So by looking for objects that do this twinkling, this scintillation, you find the quasars.
Okay, and you said you found thousands of quasars. What did you do with them?
Put them in a catalogue.
Good. What was the catalogue name? Maybe I've been using it.
No, you probably haven't. There was actually already an existing catalogue of radio sources, the third Cambridge catalogue, and we were able to see that one's a quasar and that one's a quasar, that one's not, that is, that's not, that is, as you go down the catalogue.
All right, but I think you also found some other interesting signal with the radio telescope you were using.
Yes, I backtracked just a little bit. I never expected to get into Cambridge. This was, to fill in, putting in an application was filling in the time before I went to Australia. And when I got to Cambridge, I knew I shouldn't be there. Everybody seemed incredibly bright, strutted around as if they owned the place and had an absolute right to be there.
Right.
And I'm female. There are very few women. I've come from the north and west of the country. I'm not from the affluent southeast and I'm not from an expensive school. So I really felt an outsider. And I thought, they've made a mistake admitting me. I'm not bright enough to be here.
So this is kind of what we now call imposter syndrome,
Exactly, yes. My reaction was not to run away, thank goodness, But I said, they have made a mistake admitting me. They're going to discover their mistake. They're going to throw me out.
Mm-hmm.
Until they throw me out, I will work my very hardest so that when they throw me out, I won't have a guilty conscience. I'll know I've done my best.
Oh my gosh, I just got goosebumps hearing that because, I mean, I think it's the experience of a lot of people, right? And I don't know, I can certainly say for women as well, you know, I think I've felt that every step of the way in my career is I'm an imposter. They're going to realize any second they're going to tap me on the shoulder and say, sorry, we made a mistake. You're not meant to be here. But yeah, I just kept going. And in the meantime, you're like, well, I guess I'll just do the best I can while I'm here.
Absolutely. And it's a very good ploy.
Exactly.
It's a very good ploy.
We tricked them all, Jocelyn.
Yeah. So I was being very thorough, having got the telescope working and collecting data. Our data at that time came out on rolls of paper chart. And I had several miles of the stuff by the time I'd finished. And I got used to identifying the quasars.
Of course, because this was the 60s and you didn't have computers, laptops like we have today.
The University of Cambridge had one computer.
Right.
It had memory comparable to your computer, your laptop's memory.
Right.
It took up a whole room because it was made with what we call valve, what the Americans called vacuum tubes.
Mm-hmm.
Transistors were very, very new. And we didn't use them in radio astronomy, for instance, you know, the unreliable, noisy. We use valves, vacuum tubes.
Okay.
And computers similarly. So a computer with a memory like your laptop took a whole room. And the University of Cambridge did have one such computer, but obviously very limited memory and we couldn't get time on it. So it was hard copy, paper charts. And analysing paper charts by hand.
So this is like a printer that is printing out these rolls and rolls of paper.
Rolls and rolls of paper, yes.
And you have to look at it by eye and by
that's
hand.
Right. Yeah.
Okay, and what did you see when you looked at that?
Well, I found quasars, which was good. Also found a lot of radio interference because a great big radio telescope like that picks up everything.
Yeah.
In those days, cars were badly suppressed. So a car driving down the local road could give you interference. So you get used to identifying quasars, identifying interference. But just occasionally there was another signal, very low level, but another signal that I couldn't make sense of. And I kind of filed it at the back of my brain, you know. And then one day I came across it again and your brain said, you've seen something like this before, haven't you? You've seen something like this before from this bit of sky, haven't you? And then it's easy. Because we're storing the rolls of paper in shoeboxes labelled by declination, the strip of sky. So you get out the shoebox for that strip of sky and you spread out all the old records. You need an enormous space. But all the grad students were in an attic and we had a great long floor corridor between our desks. So you spread out these charts and then you line them up so that the same bits of the sky are all lined up. And okay, here's the signal I've seen just now. Wasn't there the last time I looked at that bit of sky. Might have been there the time before. It's very low level. No. Yes, it was. Yep, clear signal there. No. Yes. And when it's there, they're all at the same right ascension, as we call it. They're all from the same bit of sky. So it's something that's going round with the stars, whatever it is. I showed my supervisor these funny signals. And he basically said, you stupid ass. He's a very positive supervisor.
Uh-oh.
This is all jammed into about 1 centimetre. Half an inch, folks. We can't see what's going on. We need an enlargement. And the way you get an enlargement when you've got these paper charts is you run the chart paper faster underneath the pen and it all gets spread out. So that's your enlargement. But I couldn't run the chart recorder at that speed all the time or it'd get through a whole roll of paper every 20 minutes. And guess who'd live at the observatory putting a fresh roll of paper in every 20 minutes. So I had to go out to the observatory shortly before that bit of sky was in the beam being looked at, switch the high speed and then switch back. And the first few times I did that, it wasn't showing anything. The thing, whatever it was, had disappeared, which of course is the grad student's fault. But then one day it performed and I got this series of pulses. It went blip, 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 blip. And I phoned up my supervisor. I thought this was interesting enough, and basically said, oh, it must be interference. I'll come out tomorrow. Or maybe you've wired the thing up wrongly and we'll see what's going on. So next day was a bit heart-stopping because this thing had disappeared until it had appeared yesterday. And was it going to appear for a second day? My supervisor watches as I wire it up and he agrees it's all okay. And we wait and in comes blip, 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 blip. And we quickly ascertain it's beating at the same rate as it did yesterday. So it's got bags of energy, whatever it is. It's not getting tired. And Tony also points out that the pulses are quite steep-sided, which implies it's something small. But it goes round with the stars? What on earth could it be? Could it actually be other astronomers? Is there an experiment going somewhere in Cambridge that's creating some radio interference? So we contact all the other astronomers and no, of course we're not causing interference. And meanwhile, I keep observing this thing. And it keeps the same period. It does not get tired. I'm now measuring the period to many decimal places.
The period means how often it does the blip,
the beat
right?
rate, yes. So the next job is to ask a colleague and his grad student who have another radio telescope and another receiver working at the same band. Could they see it? And after a false alarm, they did see it. And it looked exactly as it looked with my radio telescope. So it's not that the grad student's doing something wrong. It's not that the telescope's doing something wrong. It's out beyond the telescopes. And it can't be interference from Joe Dokes driving home from work in a badly suppressed car, because he's getting off work 4 minutes earlier every day. And this has been going on now for 2 or 3 weeks. And his employer hasn't noticed. It has to be something astronomical. But no other astronomer will admit to making any observation or doing anything that could cause the interference. Well, Jocelyn, keep observing this. So I keep observing it. And then after about a month, I suddenly realise on my usual charts, there might be another one.
Oh.
So I tell my supervisor, because this one's going to be observed at about 11 o'clock at night, or maybe it was even 1 o'clock in the morning. And I wanted somebody to know that I was going out to the observatory on icy roads at that time of early hours of the morning. And I go out and yes, it is another one. It's beating at a slightly different rate. The first one was 1 1/3 seconds. This is 1 1/4 seconds. I remember that very vividly because later that day, I was going back home to Ireland with my boyfriend to announce our engagement.
Oh, wow.
And it's kind of important that we both go.
Yeah.
So Tony very kindly kept things running while I was away. We duly announced our engagement and I came back early January sporting an engagement ring. I was so proud of that ring. I wore it to work, which was darn stupid.
Oh, really?
Because it sent out a message that I was getting married and leaving science.
Oh, no.
Because married women didn't work.
Oh, no.
But I hadn't fully twigged all that.
Right.
So I was proudly wearing this ring, which fairly quickly got spotted. When I get back, there's a great big pile of charts on my desk. Tony's done the observations, piled the charts there. Tony's in a meeting. It's quite obvious what I have to do. I do some chart analysis. And I'm busy working through some chart analysis, almost at the end of one of the rolls of paper. Oh, yep. Which one's that? It's not either. It's not either. Is it a third one? I'll just finish this roll of paper and then I'll go back through all the previous records from this bit of sky. So there's about 2 foot, 2/3 of a metre left to go. So I pass on that one. Eh? Another one? 2 on the same chart paper? 70 centimetres apart? What? At that point, my supervisor appears and stands at the end of the desk and says, Tony, look at this, look. Oh, thank you, Tony, for keeping the survey running. Happy New Year, Tony. Look at this. Huh. How many more have you missed? Go back through all your old records. So I did, and meanwhile we confirmed numbers 3 and number 4. And I went back through all the old records and didn't find any more. But we've now got 4 of these things.
Wow.
So we wrote the first one up for publication because we had most data on that. and said there were several more and we'd be doing a paper on that shortly. Tony gave a colloquium just a few days before the paper appeared, gave it a very titillating title, and every astronomer in Cambridge came. We'd been very quiet about this because we thought Jocelyn was doing something stupid, you know. Gradually, Tony and I would speak very quietly to some colleagues to see if they had any ideas about what it might be, what other tests we could do, this kind of thing. But very few people knew about it, so everybody came to that colloquium. We had two possible pictures at that stage for what these things could be. One was a very compact type of star called a white dwarf, which might be oscillating and launching shocks into its atmosphere, which somehow gave bursts of radio waves, pulses. Or it could be something rotating, and there was a beam of radio waves, a bit like a lighthouse swinging around and shining in our faces on our radio telescope once every revolution. Tony preferred the oscillating white dwarf model. And as he finished up this colloquium, he said he thought it probably was an oscillating white dwarf star. The first person to speak after Tony finished was Fred Hoyle. Fred wasn't really very happy with what radio astronomers were doing.
Okay.
Fred believed that the universe did not have a beginning, that there was what was called continuous creation.
Right.
And the other radio astronomers in Cambridge were suggesting that actually the universe had a beginning.
The Big Bang, right?
The Big Bang, which turned out to be right. So Fred didn't really like the radio astronomers.
Okay.
So with that as background, he's the first to speak. And he says, "This is the first I've heard of these things," in his Yorkshire accent. "I don't think it's a white dwarf. I think it's a neutron star." And it turned out he was right.
Right.
And he had digested all that information and hit the right explanation in under an hour.
Wow. That's pretty impressive.
So that's really where the story ends. We wrote up paper with the other three fairly soon after, and the rest is history.
Wow. Okay. But I mean, I think my mind's a little bit blown. I need a moment to recover. Okay. Let's start with this question. At any point, did you think this might be aliens?
With just one, it might have been. I gave it the name Little Green Men, LGM, but it really wasn't a serious one.
Right.
And as soon as you have a second, it's not aliens. There can't be that many aliens.
Yeah.
Let alone a third and a fourth. This is a new kind of star that we've stumbled over.
And so how did you feel when you realised what it really was?
Oh, it was exciting.
Yeah.
It took some time before there was consensus about what it was, but yeah.
Great. And why was this such an important discovery?
Because these type of stars, neutron stars, some mad, crazy theoreticians had talked about them, but, that didn't mean they existed. Well, actually, they did exist. These are they.
Okay, so this was the first evidence that neutron stars existed.
Yes.
Wow. And maybe you could just explain a little bit about what a neutron star is.
Well, a neutron star has the same mass as an ordinary star. For instance, the sun is an ordinary star. Neutron star it's marginally more massive than the sun, but only fractionally. But it's all collapsed down into a ball that's 10 miles across, 10 kilometers radius. So it's very, very, very compressed, very dense.
And why do they pulse? Why were you seeing these pulses on your pieces of paper?
They pulse because they have a very strong magnetic field. And like on the Earth, magnetic north is not at the geographic North Pole. There's a great beam of radio waves, like a lighthouse beam, coming out from the magnetic north. And so as these things spin round, they spin a beam around the sky. And we just happen to be in the right position to see that beam, to have it shine on Earth once every revolution, once every 1 1/3 seconds.
And so why was the signal there sometimes when you looked at that part of the sky, but not at other times?
Because the amount of signal coming from the pulsar wasn't that steady. It fluctuated a bit. The thing kept rotating, but sometimes the radio emission was low level, sometimes strong.
So sometimes the signal was just too weak for you to be able to detect.
Yes, exactly.
Okay.
Yeah.
All right. So this has had quite a big impact on astrophysics and our understanding of stars and their evolution and compact objects. So, what happens at the end of stars' life and what can happen after that. So this was a really major deal, which eventually led to the awarding of the Nobel Prize in Physics for the discovery of pulsars, of which famously you were not awarded that. Tell us about that.
By the time of that award, I was working in X-ray astronomy, and I vividly remember the day of the announcement because you do X-ray astronomy from satellites. And early that morning, our satellite had launched. We'd all come into work early. We didn't have a video link, but we had an audio link to the launch site, and we heard the countdown and the launch and so on. And it was a superb launch of that Ariel 5 satellite. And the launch was about 8 a.m. and by 10 a.m. it was clear that it was up and beginning to work, and we all gradually disappeared back to our offices. And the computer people were saying, we'd better get that program working. It looks like the satellite's successful. And then just after midday, a colleague came racing into my office. Have you heard the news? Have you heard the news? Oh God, the satellite's gone.
Oh no.
But it wasn't. It was the announcement of the Nobel Prize.
Right.
The award to Tony Hewish and Martin Ryle, two Cambridge radio astronomers.
Right, one of whom was your supervisor,
One of whom was my past supervisor, yes. I think John, who bore the news, expected to see me furious, but actually I was pleased.
Right.
I'm quite a strategist. Until then, the Nobel Physics Prize had never gone to anything astronomical.
Really?
And there's no astronomy Nobel Prize.
Wow.
The Physics Prize is the only one that astronomers might get. And that was the very first instance of the Physics Prize Committee recognising that there's good science in astrophysics.
Yes.
Yeah.
Yes. What a moment.
So I recognised that immediately and realised it was an important precedent and that in due course other astronomers would get the Physics Prize, which they have.
Yeah,
Quite a lot, yes. But that was the very first instance. That was Ryle and Hewish. So it was a momentous day one way and another. The launch of our satellite successfully and the announcement of the Nobel Prize.
Yeah.
To continue the Nobel story, a few years later, the Nobel Physics Prize was again awarded to astrophysicists and again for pulsars. Joe Taylor and Russell Hulse, two Princeton physicists, got it for their work on a pulsar in a binary system, which they used to check general relativity.
Which again was based on the discovery of pulsars.
Yes, oh yes. And Joe Taylor's a good friend of mine, and they invited me to go to Stockholm as a guest for the Nobel Prize ceremony.
Wow.
Which made the Nobel Secretariat a bit jittery.
A little
twitchy.
bit awkward, yep.
Twitchy. It's great fun to go along as a guest of a Nobel Prize winner. I think being a Nobel Prize winner is incredibly hard work.
Yeah.
Around those ceremonies and all the other talks and receptions and things you have to do. So that was a good way to get to Stockholm.
Okay, so you got to I assume it's a big dinner or an awards ceremony or something.
All of that,
okay.
Yes. And more.
Right. Okay, so you went to the ceremony, not as the winner, but as a guest, and it made the committee jittery. Why was that?
There had been quite a furore about my not being included in the first Nobel Prize. And I think the Secretariat were maybe feeling a little guilty or something.
Yeah.
Or anyway.
And at the time, you said you were not angry about it?
No.
Okay. And now?
No.
No?
You can do very well out of not getting a Nobel Prize.
Right.
If you get a Nobel Prize, it's fantastic. But it's so fantastic, nobody else gives you anything because they don't feel they can match it.
Right.
If you don't get a Nobel Prize, you get everything else that moves. It's much more fun.
And you have gotten everything else that moves. Which
Yeah.
is very well deserved. So in particular, in 2018, you were awarded the Special Breakthrough Prize in Fundamental Physics. And I'm quoting from the website now, for fundamental contributions to the discovery of pulsars and a lifetime of inspiring leadership in the scientific community. How did you feel about being awarded that prize?
Yeah, well, again, this is something that needs pretty fast action. If somebody knows you've got $3 million, they'll be phoning up asking for something by tomorrow.
Yep, and the prize money was $3 million, which is actually more than the Nobel Prize, isn't it?
depends on the conversions. I
Okay,
think. But
okay,
anyway, yes,
yeah.
it's big. It's
Yeah.
big. I had a little bit of warning before the announcement and did some rapid thinking about what I could do with this money because I didn't need it myself. And I thought this is a chance to do something useful to make a difference. So I ended up giving the money to the UK Institute of Physics for a scheme to fund grad students who were from minorities, students who were minorities in physics, which of course includes women, but other minorities as well.
Wow.
And they agreed to do that, and the program's been running for several years now. They're typically awarding about 10 studentships a year, 10 PhD studentships. They often go to women, but there are other minorities recognised, like disabled men, for instance, people of colour. So I'm trying to increase diversity in physics departments. I reckon I felt out of place in Cambridge because it was all white men from expensive schools.
Yeah.
It was not diverse.
Right.
If you can increase diversity in physics departments, that'll be good for the physics department. But maybe also these diverse people who are given a chance to do a PhD will also work very hard and make discoveries.
You know, maybe discover something as new as a pulsar and what else could be in the future. I mean, that's absolutely right, because if you have diversity, you have a whole diversity of thought as well, and ways of working and ways of doing things. And of course, that's what you need to make new discoveries.
Yeah, yes.
So I think this is just so amazing. Jocelyn, thank you so much for donating this money to such a wonderful cause. So on that topic, do you have any messages in particular for our listeners who might be from underprivileged backgrounds or minority groups?
It can be difficult if you are in a minority group of any sort, but I'd recommend just doing the best you can do. You can't do better. And if you work hard and do your best, maybe you too will make a major discovery.
Yeah, absolutely. And I liked what you said earlier about the imposter syndrome and, you know, working hard in the meantime anyway, even if you sort of believe you're an imposter. I just wanted to go back to science for a moment. What other scientific areas have you been working on throughout your career? You mentioned also X-ray astronomy.
Yeah. Quite a lot of my career, in inverted commas, was when I was following my husband as he changed job around the country. So after radio astronomy, I went and worked in gamma ray astronomy for a bit. And then he moved job again, and I moved to X-ray astronomy. And then he moved job again. And I went to infrared and millimeter wave astronomy. Because I was the trailing spouse, I was usually writing begging letters to the head of an astronomical institute saying, I'm moving to your area. Might you have a job? Preferably part-time, because I've got a child to look after as well. So it was a very curious career with all these changes of wavelength, quite often part-time working and quite often, you know, jobs on the technical staff or a data assistant or something like that. So it wasn't the sort of normal male career pattern.
Yeah, but you've made it work. And I think like there's something to say for the work you're also doing, raising a family as well. And I think maybe that's not valued as well because you're obviously developing other skills at the same time. Okay, have you been involved with the Meerkat telescope at all? Of course, we've got, in the lead up to the SKA, we have the Meerkat telescope in South Africa, and there is the ASCAP and MWA telescopes in Western Australia.
Yes. I was involved in some of the early committee work, pre-Meerkat. Remember learning about radio interference and how that might be mitigated, for instance, in South Africa. The railway lines needing to send radar signals along the line and, you know, farmers needing electronic equipment and all this kind of stuff. So astronomy makes some demands on local communities that way, but I hope it also brings benefits, brings a lot of people into the area, and I hope particularly helps younger people in these areas see that there are more options in life than perhaps they'd previously realised.
Yes, absolutely. That's what we're hoping for as well. But you didn't have to lay any cables or anything for the Meerkat this time.
No, it was committee work.
Committee work. And are you excited about the SKA?
Oh, yes, yes. It's going to make a big, big difference in astronomy. It's good to be thinking globally as well, the way SKA is, because I think that's the way we've got to work in future. So, yes.
And what are you hoping it will discover?
I don't know what it'll discover, but I'm sure it'll be fun.
The unknown unknowns, that's always the most exciting part, I think, as you have already shown us. And, you were mentioning that with these telescopes, it's always great to get to involve the local communities and to reach out to people who maybe weren't traditionally from backgrounds involved in science and astronomy. You're involved a lot in science communication. Why is that, and what sort of things do you do?
I do a lot of astronomy talks to all sorts of audiences, everything from primary schools to pensioners groups. And I very much enjoy doing it. I enjoy explaining in ways that those people can understand the kind of things that we're finding. Astronomy has changed hugely in my lifetime. The wealth of stuff we now have is fantastic, which also means it's been a very exciting ride as, new things have rolled in. And I try and communicate some of that excitement as well, because taxpayers basically are paying for this in the long run. So I think we need to keep in touch with the public, the average member of the public, and try and explain what we're doing and what we're finding and how important it is.
Yes, absolutely. And well, we agree here on the Cosmic Savannah. That's why we are doing this podcast. Thank you so much, Jocelyn. Do you have any final messages for our listeners?
Thank you for listening.
Well, thank you very much for joining us on the Cosmic Savannah, and a big thank you for everything you've done for women and people of minorities in astronomy and physics. Thank you very much.
Thank you, Jacinta.
You're welcome.
You're still starstruck. I mean, you could hear it in the interview.
Was it that obvious?
Yes, it was.
Yeah, I mean, you can hear I stumbled over the first sentence. I was hanging on to her every word. I had Dan, and Dan helped me prepare the questions in advance because, usually we kind of do maybe some preparation, but we kind of just have a conversation and it's quite natural. But this time I didn't want it, my mind to go blank and get starstruck. So we prepared all the questions in advance, and I really enjoyed it.
Yeah, she was very patient too. I mean, just as we said in the intro, an incredible person, and what she's achieved and what she continues to achieve, and her commitment to astronomy and advancing astronomy in all the ways it needs to be advanced, not just with the research, but also with increasing diversity and development of young astronomers.
Yeah, and I also liked how she also alluded to having an imposter syndrome, because this is something that we all deal with at some point in our lives. So just keep working hard. And until, they don't see that I don't work hard enough, or until they kick me out, I'm going to work as hard as I can. And I think that is very important for us to just keep on working hard and doing what we are passionate about.
Absolutely. And I think that almost all of us suffer from imposter syndrome. Yeah.
To some extent or another. And I mean, it sounds like she had it worse than most, even being the only woman in the department and really going through.
Yeah, I actually can't imagine how hard that would have been.
Yeah, sure. Yeah. But
it's inspiring to hear somebody who's overcoming the odds of being a minority and, really making it. Really exciting.
Yeah. Thank you for the interview and for taking the opportunity to chat to her.
You're so welcome. All right. So I guess we're near the end of the episode, and we traditionally like to end by saying, how are we all? And what have you been up to and what are you doing? Dan, do you want to go first?
Sure, I can go first. Yeah, very busy, as always. Get tired of saying that, but I'm off to Poland now to the European Astronomical Society meeting, which I'm quite excited about. There'll be a lot happening there. We are promoting the General Assembly in Cape Town next year. So I'll be giving a talk. We have a special session on the General Assembly. I'll also be promoting the podcast.
Ooh, yay.
I have a Cosmic Savannah poster, and as we mentioned at the end of last season, we have stickers.
Stickers!
So if you are at the EAS, pop by, grab a sticker.
Have we given you a sticker yet, Sia?
Not yet, and I think I should actually have one now.
Okay. Oh, that's very rude of us. Okay, we have to fix that immediately.
Immediately after this. Yeah, so I'm heading off to Poland, which is also really cool, a little bit tense and Busy. So yeah, it's travel is always a little bit stressful, but looking forward to it. I think it'll be really great, and also just to reconnect with some of the friends abroad who will be attending, and hopefully come back with some cool stories and some cool learnings.
Looking forward to hearing what you experience.
Who's next? Sia?
So first, how am I? I think I'm doing pretty well. Sometimes I like saying I'm coming out of a low, but actually now I've been pretty good for a while. And recently now I actually have to be at the OAD once a week. And I didn't know that I needed to be.
Oh, so you're coming into the office again?
No, I'm coming into the office at least once a week. But I think it's been a very great working environment for me and outside of UCT where I did my PhD. So I think that is really working well for me so far. And we're also planning an astronomy education workshop for teachers and astronomy coordinators and science center personnel that will be happening in Cape Town. And also that is just working up to the GA as well. So that's what I've been working on. And I think it's going to be exciting to see what contributions can come from there and can be important for astronomy education going forward.
Yeah, that sounds amazing. The GA, that's the International Astronomical Union's General Assembly, which is being held in Cape Town in 2024.
That's going to be exciting.
Yeah.
That's like the Coachella for astronomers.
Yeah, that's true.
That's so much better than the World Cup. Everyone says it's the World Cup for
the
astronomers.
Coachella, I like
Coachella,
that.
yeah, I like that.
So it sounds like
Glastonbury.
Sounds like you've really got your work cut out for you at the moment as well.
I'm trying. And you, Jacinta?
Yes, I'm great. Still quite refreshed from my trip abroad. As you were saying, Sia, it's always great to change environment. If you feel a bit stuck or, bogged down, and change environment and you get a bit of a refresh. And so it was really great to be working with some collaborators over in the UK. And then I went on a 2-week holiday to the Croatian coast, visiting my friends. Those who listen to this regularly, I used to work and live in Croatia for 4 years. And because of COVID and such, I haven't been able to visit. So it was great to go back and visit them, be in the Northern Hemisphere where it's summer, and lots of fun. And kind of got a little bit of the post-holiday blues once I got back into Cape Town where it was raining. But, I'm out of that now, back into the swing of things, and very busy preparing my lectures, which are going to start at the end of July. My lecture course is for all of the semester, and a bit nervous about that, but looking forward to it as well.
All right.
Okay, so I think that's everything for today. This was a great episode for many reasons. Our new host, back in the studio, season 5, really awesome guest. And so thank you very much for listening, and we hope you'll join us again for the next episode of The Cosmic Savannah.
You can visit our website, thecosmicsavannah.com, where we'll have the transcript, links, pictures, and all the other stuff related to today's episode.
You can follow us on Twitter, Facebook, and Instagram at Cosmic Savannah. That's Savannah spelled SAVANNAH. You can also find us on YouTube, where audio-only episodes are uploaded, with closed captions which can be auto-translated into over 200 languages, including Afrikaans, Xhosa, and isiZulu.
Special thanks today to Professor Jocelyn Bell-Burnell for speaking with us.
Thanks to our social media manager, Sumari Hetting, and also our audio editor, Jacob Fine.
Also to Mark Walnut for music production, Michal Werchek for photography, Carl Jones for astrophotography, and Susie Karras for graphic design.
We gratefully acknowledge support from the South African National Research Foundation, the South African Agency for Science and Technology Advancement, the South African Astronomical Observatory, and the University of Cape Town Astronomy Department.
You can subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts, and would really appreciate it if you could rate and review us and recommend us to a friend.
And we'll speak to you next time on The Cosmic Savannah. Someone's breathing.
No breathing for 10 seconds. Okay.
Okay,
Start again.
pull yourself together. Okay, we're starting 10-second silence again.